Welcome back, everybody. I hope you enjoyed the break and the FISCON presentation. I'm actually going to give a talk there about quantum physics, in case you're interested about this. So we are now already in part 4 of the, I was about to say 3, but no, it's already 4 of the big data course. Distributed file systems, so you see the blocks here going across machines. So this is going to be the focus. But it's again blank. before we do this, I will ask you a question. I don't know what's going on today. All the computers seem to be unwilling to work. But anyway, that should work again. I just need to put it back on the screen. I think it is recording. Can you see it? I think it's recording. All right. So this is my question to you. What is the, among these 4 answers, what can you not store as a single object? And now I realize why you were all surprised that it wasn't actually a project. When I tell you something doesn't work, then everything doesn't work. So let me just open this other window. It's because the application crashed, and of course this crashed too. So I make sure that you can see it. And now I think we are back to normal. You can see the codes where you can connect, and everything should be back to normal. So which one of these can you not store in S3? Is it the first episode of Star Trek Discovery? Is it the 300 petabyte data set of the collisions at CERN with the Higgs boson, static page of a website, or an archive backup of your 2 terabyte hard drive? All right, so we have a majority. And here I even show you the answers live, right? I think before we didn't even show them, but at least you have an agreement. Be careful, the majority is not always right. But here the majority is right, indeed, 300 petabytes. Why can we not store this as a single object in S3? Exactly, it's a limit of 5 terabytes per object in S3, if you remember. The order of magnitude matters. It's what fits on a typical hard drive. All right, so indeed, the rest we can, but not CERN, and we'll see today how we can do it. And then we have this other question, how things seem to be working again. Do you remember what I told you about the best practice between scaling up, scaling out, or trying to write better codes? So we have a majority as well. And here too, I agree with the majority. Of course, that's a rule of thumb, right? There's always exceptions depending on every use case and so on. But globally, the first thing you should try is do it at a small scale on your laptop and try to improve the code, the memory footprint, the code and everything. And then you take it to the cluster and then you can scale out. It's really a great feeling. That's something that a lot of PhD students experience. This feeling you have when on your own computer, you try to, you manage to make it like twice as fast, and then you take it to the cluster and you realize it takes only 1 hour instead of 2. And that's a great feeling to have. So always worth trying to fix the code locally on your laptop first. All right, and then you scale out because that's linear in cost, and scaling up is not linear. It actually, the more memory you want and CPU you want, the more expensive, the higher the marginal costs are. Trying to adjust the audio because I feel maybe it's a bit loud. All right. Okay. So now that we have taking care of these two questions. I'll continue. So we rehearsed 2 weeks ago relational databases, SQL, normal forms, and so on. Then we saw that we can scale out on a cluster of machines. We can have thousands of machines on which we can distribute the job. We already used that scale out on the cloud storage, on key value storage, when I showed you Dynamo and the ring with the key values. It's also used in S3. We just don't know how it's done, right? It's not very documented. The only thing that I know is that they use a lot of microservices. So they have plenty of teams working on various sub-projects, and there's plenty of interacting components that orchestrates the whole object storage service at Amazon. But we don't know much. And so this is why now is going to be the first time that we actually see the internals of a system at a large scale that stores data sets. So we've seen object stores, key value stores. Remember, object stores is like S3, Azure Blob Storage, can be very large objects, terabytes. Key value stores, that's typically at most a couple of hundred of kilobytes per value, much, much smaller. And that's peer-to-peer. That's all distributed in the way that we saw. Now we are going to have a small shift. You remember that in object storage, we could have billions and even trillions of objects, but these objects cannot be larger than 5 terabytes in the case of S3. Who remembers that? Right, okay. Billions or trillions because it's a worldwide service for the entire world, that's why. So billions of terabyte files. We have object storage with the key value model. The key value model just means we have bucket plus object IDs and we have the values, not to be confused with key value stores, which is specifically Dynamo and what we saw in the second part. So that's what we did last week, be today. Today, the focus is going to be on millions of files that can each be up to petabytes, right? So this is the focus. Billions of terabytes files, millions of petabyte files. So we are going to look at a different paradigm where we are going to have file storage as opposed to object storage and block storage. We saw a few blocks last week, but now I will tell you more about the blocks. It was in the context of Azure. Okay. So it all started at Google. Google needed a way to store a lot of data, but it didn't fit on single machines. So at first, you can hack something quickly, right? Connect a few hard drives, connect a few machines, but then you quickly realize that if you don't think it through, and if you don't come up with a well thought through architecture, that's going to cost a lot of money. So this is why they invented GFS, the Google File System. That's in the early 2000s. So that's more than 20 years ago. And the idea behind this system is that if you have one computer, your computer might crash. Your computer might completely break, and you need a new one or a new hard drive. But on a very large scale, it's not just that it might fail. If you have thousands of machines, is that it will fail. Small experiment. For whom has ever the laptop completely crashed once? You see, it's guaranteed. There's 500 of you. It's guaranteed. It's the indicative tense. It will, the future, it will fail. That's the same idea in the data center. If you have thousands of machines, they will fail all the time. You even have people working full-time there that just keep replacing the drives, the memory, and so on in order to keep it running. And so from the moment you want to have such a large file system, you have to account for the fact that it will fail, and it will even fail once in a while. So on the very high level, the idea is that we first want to monitor the system. We want to know when a computer crashes or some disk is corrupted, the data is corrupted. We want to detect that an error occurred, automatically recover from it seamlessly, and that gives us fault tolerance. So we want a fault tolerant system that continues working even if computers crashed. In fact, we've already seen a fault-tolerant system. Dynamo is a fault-tolerant system. You can have nodes that join or leave the network, and it continues to work. And we saw with the sloppy quorum and the fact that you ignore the unhealthy nodes and just go further down the list to find healthy nodes. So this is also a fault-tolerant system. But here we are not talking about a key-value store. We're talking about a file system, a distributed file system. What does that mean? So first, we are not talking about values of 400 kilobytes. We're talking again about gigabytes, terabytes, petabytes per file. So I will tell you the features we want in our gigantic file system and what we do not want. You know that on your laptop, you have random access to the disk, right? You can modify a file, any bit, any byte in a file, you can modify it, right? You can also read anywhere within a file. You don't need to read the entire file. This is called random access. In our file system, we don't care about random access. We don't care about efficient random access, to be more precise. You could still try to have random access. It's just that it's unusable. It's going to take forever. So we don't care about random access. What we are interested in is scanning files. We want to read through the file. While, because it's big data, we want to run data analytics. We want to just scan through the data, aggregate it, analyze it, right? So we want to scan through the file. And the idea is from the beginning to the end, right? And later also in parallel. So we don't care about random access. The same goes for writing to the system. We may want to append at the end of a file. So that's okay. That's not random access. We just add more content at the end of a file. When you log, for example, for logging, or you create a new file, you delete a file, that's okay, but you do not modify small parts of a file in a random access pattern, right? Create, delete, or append to a file. For whom is that clear? All right, so that's what we want as a system. It's particularly useful if the data, for example, comes from sensors or from logs for a website, or maybe from CERN, that you're just accumulating the data that just came from the collision. So then you keep appending, right? It's just new data, you collect new data. That might also be intermediate data in the sense that we've already executed a query that wrote back to the system, and then we are going to read again from it. So intermediate data also works like this. We will see when we have MapReduce and Spark that when we output the data from MapReduce and Spark, it's also going to create file or append to files, and that's it. It's not going to have any kind of random access pattern writing back the results. One further thing we would like the system to work even if hundreds of machines connect to the system and try to use it, right? Imagine that this is a cluster of machines that is owned by a company, a large company, and they have plenty of employees that want to use that file system and store data in there. Think Google, right, who came up with that file system. They have tens of thousands of employees who might be connected to the system. Okay? So we want them to be able to do that in an atomic fashion, in the sense that they just write and create file, but it's all or nothing, right? Either it succeeded or it didn't succeed, and in parallel at the same time. Who is with me? Right, so that's just the requirements. That's what we want to have. I'm going to throw in one more requirement, and I'm going to give an intuition on that requirement. So the intuition behind this requirement is I want data to flow around in my system. I just want the network cables to be full with data that is just circulating and flowing through the system. What I do not want is a system where we just wait for things. We just wait, right? So latency. So that's the intuitive way of saying that. I want data to flow around. Formally, the way that I would describe it is in terms of throughput bounds. And we're going to have a week about that, about bottlenecks and how you improve a system. But there is one rule of thumb. When you try to make a system faster, you need to find out where the bottleneck is. Is it the CPU that's overloaded? Is it the memory that is full? Is it the network bandwidth that is at maximum, that is fully used? Is it the disk that is already at maximum read speed? It's always one of these. One of these is the reason that constrains your system. And we use the adjective bound for this. Your CPU bound or memory bound or network I/O bound or disk I/O bound. In the case of our file system, we want to be throughput bound, right? What constrains the system needs to be the speed at which the data flows. We do not want to be latency bound. We do not want the system to be limited because we are just waiting for things to happen idly. That would be a waste of resources. Who is with me? Right? And I'll come back on this because you will see we'll look at the blocks that is all connected to this. And now, connecting back to the introduction week that we had, you remember that capacity grew enormously. Throughput grew a lot, but much less than capacity. Smaller factor, and latency improved even less. And the solutions that we are going to use are parallelism, that is solving the issue between the capacity and the throughput. We are going to parallelize when we use MapReduce and Spark. And the other thing we are going to do is batch processing. Batch processing is a bit more subtle to understand. It's the idea that instead of doing things one by one, you do them in batches, right? An example is when you go and eat at the Benza, they cook in batches. They cook 100 or 500 or 1,000 portions, right, at the same time. And it's more efficient than having a Mensa in which there is a small kitchen and they cook 5 persons at a time, right? That would be less functional. Who gets the intuition of that? Right? So that's the batch processing. And that's going to reduce the latency, the discrepancy between latency and throughput. Do not worry, because these two things, parallelism and latency, they will be so all over the place in the lecture that at the end, you will have a good intuition of what that actually means, right? So now, coming back to what we are going to do, these are the Google technologies, Google File System 2003, MapReduce, who heard of that? Right, that's a paradigm to parallelize reading from GFS, 2004, and Bigtable, who heard of this one? Maybe less, that's 2006, right? These are all technologies that were invented at Google. Turns out they have an open source counterpart, and that's what we are going to study in the lecture. GFS, the counterpart is HDFS, Hadoop Distributed File System. That's what we do today and tomorrow. Then we look at MapReduce a bit in a few weeks, and that HBase, which is the Bigtable open source counterpart. White colon store is the formal name. H is for Hadoop, by the way. HBase, HDFS, H is also for Hadoop, right here. So all the three of them will cover this in this lecture. This action happened 20 years ago. 20 years ago, there was a sudden, in a couple of years, it evolved very, very quickly. All at Yahoo, so the initiator of this was Doug Cutting of Hadoop. This is the elephant teddy bear of his son, Hadoop, the name. So at first they had 188 machines, and then you see it increases. The last time we heard an official number was 2011 with 42,000 machines. They had 100 petabytes. And then there is a guesstimate, non-official, of 100,000 with 600 petabytes, but not officially confirmed. And if you remember what I told you, we are reaching the limit of the data center of a cluster of machines, right? Because of cooling and energy and so on. So it means we basically reached what we can achieve in a single cluster. Who is with me? Right? Okay. So this HDFS can work on tens of thousands of machines. This is absolutely gigantic. So now I'm going to show you how it works, but because of data independence, I'm going to first show you the logical model. And after that, I will show you how it's implemented physically. But I always start in every lecture, I start with the logical model. So that's the perspective of the user who has no idea what's going on behind the scenes. And you will see it's actually pretty simple, the logical model of HDFS. It's like this. First, unlike object storage and S3 and Azure Blob Storage, we don't have a flat key value model. We have a file hierarchy. We have directories, we have files, and we have a whole hierarchy like this that is in fact a tree, right? And the leaves are the files, and the non-terminal nodes are the directories. That's what you're familiar with on your computer, the typical file system. This is the reason we now say file and not object. Technically, it's the same thing. It's just a bunch of bits, right? But what we called object, now we call it file because we have a hierarchy of directories. So it's a file system. So that's the first thing that we have in the data model of HDFS. There is a hierarchy of directories and files. And the second thing is that instead of considering an object as just one big chunk of bits, which we did in S3, we expose the blocks to the user, meaning that the user is aware that this file that you store on HDFS is in fact made of blocks. In that case, 8 blocks that are stored in the system. So the API of HDFS allows you to fetch blocks. You can get this block, that block, and so on. Who is with me? Okay. Now about some terminology. If you look at the GFS paper and the HDFS paper, you will notice that they do the same thing, but they give them different names. That's just life. And you just need to understand the concepts. So do not be surprised if some people say chunks, some people say blocks. In this course, you will also hear a split, shard, partition. It's always the same idea. We just partition the data, right? So do not be surprised, even though there is usually a context, right? So block would be for HDFS, chunk for GFS, split for MapReduce, shard when you talk about data sets, partition more for mathematicians, or when you talk about the network partition, or Spark, we also call it partition. Here it's just, I would say, awareness of the context. If you talk to other engineers of HDFS, but you call it a split, they will be surprised because they would expect for you to use the word block, right? So again, it's a matter of context. All right, but these are just words, and we are interested in the concepts. So to summarize our data model, pretty simple. We have a hierarchy of directories and files, and every file is further divided into blocks. Who is with me? That's it. It's all on this slide. This is the logical model of HDFS. It's really that simple. Okay? But the difficulty is how we implement it to work with petabytes, hundreds of petabytes of data on thousands of machines. So you did hear me correctly that a single file can be petabyte big, right? I really did say that, and now the intuition is that it's because of blocks. Because the blocks, of course, will be smaller, and the blocks will fit on a machine, but not the entire file. In fact, the Azure Blob Storage, when I talk to you about block blobs, they kind of already introduced that in object storage, that concept of blocks, and that's what allows them to have almost 200 terabyte objects. That's just because they cut them in blocks, okay? However, Azure Blob Storage does not have a file hierarchy. It's still object storage. It's still a key value model. All right. So since we have blocks, what we are going to do with our thousands and tens of thousands of machines is that all of these blocks that we have for, let's say, all of the blocks of all of the files, we just spread them across the machines. So say I have 8 machines and I just spread the blocks like this across the machines. That's the idea, right? We spread them across the cluster. So now, quick question, but I'll not do it with a clicker, just asking you directly. I would like to see what intuition you have for the size that a block should have, given one, that the blocks also exist on your laptop and their size is roughly 4 kilobytes, right? We talked about that recently. The same for relational databases on a single machine. So that's the first piece of data that I'm giving you. And the other piece of data, remember that now we are in a cluster of machines and we want to be throughput bound. We don't want to be waiting the whole time. We really want data to flow across the network. So let's see, you can guesstimate. It's also okay to be wrong and to make mistakes. I just want to get a sense. So what do you think? How big should a block be? Yes? 4 gigabytes, yes? Same 4 gigabytes, anybody else? 100, sorry? 512 megabytes, yes, okay. Anybody else? 200 megabytes, petabytes? Megabytes, yes? Anybody else? One? Oh, 1 terabyte. Oh, you're very ambitious. 1 terabyte, okay. 1 megabyte. Anybody else? Okay. So the center of gravity is about right? Did you have another proposition over there? I think I saw a raised hand, maybe not. All right. So the center of gravity is correct. The order of magnitude is correct. We are within the hundreds of megabytes, gigabytes order of magnitudes. Absolutely. In the case of Azure Blob Storage, 4 gigabytes is the value that they picked. In the case of the Hadoop distributed file system, they take a default value of 128 megabytes. Some other flavors, it's like Linux distributions, right? There's other distributions of Hadoop file systems, and Cloudera is an example. Cloudera, I think, takes 64 megabytes. GFS, I can't remember. It might be that GFS also used 64 megabytes. I don't remember for sure. But that's the order of magnitude. And I really want you to see that 4 gigabytes, 128 megabytes, it's a factor of 10, right? It's roughly the order of magnitudes. To explain the difference between 128 megabytes and 4 gigabytes is just that time elapsed, right? So this is 20 years old, 128 megabytes. It used to be also that order of magnitude for Azure. And a couple of years ago, there was a big announcement from Azure that they say, okay, now we are moving to 4 gigabyte blocks. Why? Because hardware evolved, right? Things are getting faster. The ratios between the different hardware PCs have evolved. And now we are in a position that we can go with blocks of gigabytes, right? It could be in HDFS that they change the default and maybe it becomes also 1 gigabyte or 2 gigabytes or 4 gigabytes, right? Again, the order of magnitude. What we make of this, if you do some quick math, how many blocks would fit on one disk of a typical size? And if you do the math, a disk has, let's say, terabytes of data. How many times do we fit 128 megabytes into 1 terabyte?
You said 128 megabytes.
Yep. In 1 terabyte, how many blocks of 128 megabytes do you fit on a terabyte hard drive? 8,000, exactly. That's the order of magnitude, thousands. So if you have 128 megabyte blocks, that's 8,000. If you have 4 gigabyte blocks, that would be more like 250, if I'm correct, right? So you see, you want roughly hundreds, thousands of blocks per machine, right? Again, that's the ballpark that you need to have here. Every machine is going to have a few thousands of blocks. Okay. Everybody with me? Yes? Or you're getting asleep, or who is with me? Okay, very good. Plenty of bracelets. So now that I've explained the logical idea of HDFS, we just have a bunch of files in a hierarchy with directories, and every file is cut into plenty of blocks that now we know are 128 megabytes, maybe a few gigabytes a few years later. We are going to look at how it's actually implemented. That is really awesome to look at the fact that actually it's not so complicated. So the first question we have, since we are going to use thousands of machines, tens of thousands of machines, how do we connect them? Well, we could think of a peer-to-peer network. That's what is done in Dynamo, right? We could think of a centralized architecture, right? Where we have one node that coordinates and then all other nodes are connected. Who thinks, of course, if you saw the slides before, it's even easier for you. Who thinks it's a peer-to-peer network? Who thinks it's a centralized architecture? Who doesn't know? Okay. Well, in fact, it is a centralized architecture, right? We indeed have a centralized architecture. In fact, it's going to be the same almost every week. We are going to have a centralized architecture. So one of the nodes, there's so many names that you can give to them, coordinator, primary, main leader, and then you have all the machines that do all the work. So the worker, secondary, follower, plenty of names. So it's a centralized network because all of these machines right here, they all speak to the coordinator nodes. So the next step is that we have this centralized network. Where do we put the blocks? On the worker nodes, right? So this, I only put 3, but now you know it's actually thousands of them here per machine. So I just draw 3. And we need names for these. We are going to call the node that coordinates everything the name node, because it's responsible for the file namespace, as we will see, so the name node. And all of these nodes right here that store the blocks, we call them the data nodes because they have the data, right? The blocks, this is the data. So the data nodes. You will sometimes see it in camel case with a name node with a capital N, uppercase N for node, right? It's just when you talk about the Java classes, you might see it like this. One more thing that is conceptually important and that you need to keep in mind is that people tend to call the nodes, node is for machine, right? A node is a machine in the data center. And when we say the name node or the data node, you think of the machine. So there's a machine that is the name node and some other machines that are data nodes. If you want to be more precise than that, you should rather say that the name node and the data node are processes that run on the machines, right? So on this machine right here, that's a machine, it has CPU and memory. And one of the processes on that machine is the name node process, but maybe there's other processes too, right? But that's a process running here. And here we have a data node process running on that machine, maybe with other processes. And the same here, we have a data node process and so on. But when we speak about the system quickly, we abuse a bit the terminology and we tend to say the name node, the data node, talking about the machine. Just keep in mind that we actually mean the process, right? I think it's called the metonymy. Who is with me? Right, very good. We have a question on Zoom, go ahead.
What happens if the name node fails? How do you choose the name node?
Oh, wow, you're already taking a lot of advance because I have plenty of slides to explain these things. So indeed, we do have a single point of failure with the name node. And if I can keep that as a cliffhanger all the way to tomorrow, probably I will explain what happens if we lose the name nodes, right? But you're absolutely right that we can lose the name node, and there is some engineering behind this that still makes it work, right? So very good question. Okay. I'm not answering. I'm just saying I will answer in the course later. Yeah. Okay. All right. So let me continue. So what it means now from the perspective of a file, whenever you store a file, so a file can be very, very, very long. So the first thing you do is you cut the file into chunks. So in the case of HDFS, 128 megabytes. So we just chunk it like this. And what we do next is we store every one of these chunks 3 times. So we replicate 3 times. So I take the example of the orange one. We make 3 copies, 1 block here, 1 block here, and 1 block here, right? So I use the GFS terminology here. We store it 3 times. Do you know why? Because of fault tolerance, exactly. If we lose machines or if it crashes, then we have other copies, right? A direct consequence of this, because this is a question that is often asked, it makes no sense to use a RAID system, right? Redundant array of inexpensive disk. It's totally useless. You don't need to have RAID systems on the machines because we already replicate across machines, right? So it already handles the replication. The name we give to these copies is replica. We say that every block has 3 replicas. It's stored 3 times. The second thing to know is there is no notion of one of these replicas being distinguished from the others. We just store it 3 times, but there is no hierarchy between the 3. Okay. So every node is stored 3 times. I did the same with all others, except maybe I didn't pay attention or didn't count. I think there's even 4 replicas in here of the green one. But anyway, you get the idea. Every one of these chunks is going to be stored 3 times. We'll look later about how we distribute them or how we decide the machines, but you can think of it as just spread over the entire cluster. Okay, so that's how we have a file. And now we are going to slowly look inside what's going on inside the name node and what's going on inside the data nodes. Yep. Oh. There we go.
I just wanted to ask about the replication of 3 times. Is that a fixed rule? How do you decide how many times you replicate?
So you can decide. It's a configuration parameter, and you can change the value even per file. You can decide, I want a replication factor of 3, a replication of 4. You can change that value. What decides on the replication factor is how paranoid you are about losing data. Right. So if you really have data that you can't afford losing, maybe you increase a bit and you say, I want 5, I want 7. If you really don't care and you want to lower your cost, you say 2 is enough, or even 1 is enough if you even can afford losing it. Right. So it's something you can tune. By the way, you can also tune the block size. If you're not happy with the 128, or if you love Azure, you can set it to 4 gigabytes. Right. That absolutely is fine. You can change that value. Yeah. Did I answer your question? Awesome. Any other questions? Right, so let me continue. So now it's more about fun facts, because actually it's more like an anecdote. Oh, we have a question on Zoom too.
If the data is spread across nodes, how does HDFS handle data locality to minimize network transfers?
That's a very good question. I'll answer it also later. I was joking. Technically, you're asking very good questions, because all of these questions are addressed in the course on the slide. So it's very good that you're basically thinking exactly like the engineers of the system. The idea is that we try to manage it in such a way that when you launch MapReduce or Spark, you try to read from the same machines, because we actually will co-locate the processes for the HDFS with the processes for MapReduce and Spark. So that is the idea. And so we avoid network transfers because we try to read from within the same machine. Then there's not even network involved at all. Right. Okay. Did I not answer your question? I will come back, of course, on all the details of all of that. Yeah. All right. But these are very good questions. I mean, the fact that you ask exactly the questions, that's very, very good. It means that you're following. Yes, it's all implemented in Java. That's why you sometimes have the camel case on NameNode and data nodes. So it's all done in Java. So now I'm going to go inside the NameNode. So what do we have inside the NameNode? That's probably the last thing that I will say for today. So inside the NameNode, we mostly have 3 things. The first thing we have is that the NameNode has the file namespace. What we call the file namespace is the hierarchy of directories and files, not the content of the file, just the names, right? So it has the whole hierarchy of directories and files, possibly with access control. It knows, just like you have on your computer, there might be a user, there might be a group, there might be a read and write authorization, and so on. So that's the first thing we have. The second thing we have is a mapping for every file, from every file to block IDs. Right? So every file is associated with blocks. For example, file 1 we know it's the green block followed by the blue block, right? And then file 2 is black, purple, orange, red, and so on and so on. You see how important it is, right? Because if we don't have that mapping, we just have blocks all over the place, but you don't know how to assemble them back into files, right? So you need that mapping. You need to know which file has which blocks and in what order. Okay, so that's the second thing we have. And the third thing we have in the data node is a mapping from the block IDs to the block locations. For every block ID, we know which data nodes have a copy of it, typically 3, right? Every block ID will have 3 data nodes. I insist that in this mapping right here, this is not the actual content of the blocks because they're on the data nodes. This is just the IDs of the blocks, the block IDs, which has, it's just 64-bit integers. Okay? Who is with me? Right? Who agrees that with this right here, we have all the information we need to reconstruct the file system from a logical perspective? Who agrees? Right? Okay, very good. So we have another raised hand over there. Where is the microphone? There, small hops. Yeah.
So you mentioned that in the second system, you have IDs of the blocks, but how is it? Is it individual per type of block and then that maps into locations? Or is it a list of all IDs with all the 3 possible blocks?
So
I'm not sure if I'm clear, but.
Yeah, I think it's clear. A block ID identifies a block that might have 3 replicas. So the 3 replicas, they have the same ID, right? So these are really the unique blocks. So here you say which file has which blocks, and then here you say for every block ID, which are the machines that each hold 1 replica of that block. And then you can go ahead and ask the machines. Did that answer your question?
Yes.
Yeah, awesome. Any other questions? On Zoom? Okay. All right, so tomorrow I'll continue telling you what there is in a data node, even though you already know these are blocks. And again, do not worry about the questions that you ask. I will show you how we place the replicas. I will show you how we handle the locality. I will show you what happens when the NameNode crashes. Thank you very much. Thank you, Sarah, for the moderation, and see you tomorrow.